So here's a case where the textbook, both editions, were very consistent, but I think they made things much more complicated than I think they need to be. So what I'm referring to here is, of course, there's that section on linear regression. We've all done our determination of y equals mx plus b before, but we also know that you just typically plug it into your calculator and it pops out slope and intercept and you've got things ready to go. Or you put it into Excel and you graph it. Or if you're able to be slightly crude about it, you plot your data, you do your best fit with your ruler through it, and you guesstimate the line, but we know that's not the proper way to fit it. For that, you actually look at the residuals and figure things out. Well, they talk you through that, and they even bring up using matrix algebra to do so in some of the chapter. I'm not going to worry about specific page numbers. That's a little overwhelming. But when you get through that whole section, finally you get to a sub-portion called How Reliable Are Least Square Parameters. Now that should be something we care a lot about in this course. Let me point out why. Whenever we set up a regression line, what we're doing is we're making the assumption that x is known perfectly, that there's no error in x, but that y, our actual measurement, has error associated with it. So if we wanted to think of it like this, we're going to have a little Gaussian distribution for each of the points along it that we measure. That didn't look very Gaussian, but just go with it. Yeah, something like that. So we have all of our little Gaussians right here, and they should be straight up and down. I just can't draw that well freehand. So we're going to have that uncertainty along this line, which means that there's going to be some uncertainty for the intercept. There's going to be some uncertainty for the slope, and there's also going to be some inherent uncertainty that describes the amount of scatter we have for these points. Now, our textbook is going to go through each of those three pieces like so. We're going to find SY. Now, we also got to point out that this DF comes from here. What they've done is they've tried to make sure that they separated things out very well so you could really see exactly what was going on. Now really all they're saying here is this is how far each point is away from where you'd expect it to be on the line. That's really what we're saying, because if y equals mx plus b, if you rearrange that, this would be your predicted y. This would be your actual y. You subtract these two, and that gives you the deviation, the difference, however you want to think of that. Now that said, why not just combine the two? And let's just see here in our equations book. SR is the same thing as SY. These are the exact same equation. It's just that what we've done is we've brought that term in, and it's actually part of this equation. I just wanted to point that out because it's one of the important distinctions that you'll see. But all of our lab manual handouts continue to use S sub R. You'll find S sub R used in other textbooks as well. And it's the one that seems a lot more familiar to me. So I'm going to go ahead and keep with S sub R. But please keep in mind that S sub R and S sub Y are exactly the same thing. It's just that with S sub R, you don't actually have to sit here and do this as a two-step process. But you'll notice the rest of it, the equations would be the same. Now when we get to S sub m, that's obviously going to be the standard deviation of the slope. And S sub b, y equals mx plus b, that's where the subscripts are coming from. This will be the error of our intercept. Actually, let me be rigorous. That's the standard deviation of our intercept. So if we take the square of that, it should equal the square of that times that divided by that. Or we could keep things really well built in. So S sub m ends up having this form, and S sub b has that form. I find these two to be much simpler to use. Especially notice that if you were setting this up on a spreadsheet, you can set this one up pretty easily and calculate S sub r. You can then plug S sub r into any spot where you need it in these two equations. Right here at the top, right here in the front, and you're ready to run. That's what I find to be the easier way to handle these sort of standard deviations from the regression line.